let's figure a few looks. This extreme variables in VWV, the complete sample with delta PS over 4 seconds.
Okay, yeah. So thanks very much to Javier and Lee particularly for this. So what I'm showing is mostly classic case of experienced researcher taking the hard work of other people. Javier developed Dopot, which works really fast, which we can all use, and Lee did this incredibly hard work of VIRAC version 2, which 99% him. And it's created light curves for everything. And since he's most interested in the astrometry, well, I thought someone has to go and look for the high amplitude variables, which some of us have been interested for a while, and do a systematic search for seeing what we find. Part of my motivation for this is that the largest group is usually young stellar objects, which is kind of my area. But there's a lot of us here who've been working on this for a while. Okay, let's try and get this to pick up. Yeah. So Lee talked about VIRAC, so I don't need to say too much about that. Tell a bit about the YSOs, and then more generally about what we've got, everything that we found that's over 4 magnitudes in the working database, and the kind of conclusions we're getting to from this. So basically finding things which have variable, in the YSOs at least, things that have variable accretion, things that have extinction, occultation events, and there are explosions in star formation regions, which I've been quite interested in, spending a lot of time on over the last year or so on those. Okay, so this is VVV. My talk at VIRAC version 2 is entirely based on the blue area, the original VVV area. So it's not, the database does not include VWVX yet. That's work still to be done. Right, that was cool, yeah. Okay, so some background on young stellar objects is that most pre-main sequence objects are variable. Okay, if you look with high quality CCD time series, you could detect variability more than a typical main sequence star. Obviously, if you look with Kepler, every star is variable, so it's a moving definition. But typically, this is like, you have magnetic cold spots, you have hot spots, which are often caused by accretion columns. You have matter, which is a magnetically levitated, often accretion disk, and follows a column above the plane of the star system and lands on the surface of the star, creating a hot spot. So these rotate around at the same time as the cold magnetic spots, which are quite large on pre-main sequence stars. They also give you some variation in the visible light. And then you also get changing extinction and changing accretion. So optical light curves in particular, and to some extent infrared light curves, are a bit of a mess because you have all of these processes, the rotational processes, changing extinction as matter orbits the star, and variable accretion rate on, usually on short time scales, but in recent years people noticed it varies on long time scales as well. So it's actually a bit of a mess trying to sort out what is causing the variability. And Jen actually did his PhD on 1 or 2 particular YSOs where he looked at in detail at how can you tell by looking at a color magnitude diagram which of these mechanisms is correlating with variability. He was able to show that they have different behavior in color and magnitude. And so at least in visible data, it's possible to tell the difference. So the colors are useful for that. Okay, but my interest is the extreme variables. So historically, there are only a few of these eruptive variable YSOs, maybe sort of about 20 or so in tops of what we call FU Orionis outbursts, and XOR is the other kind. So the FU Orionis types are named after FU Ori, was the progenitor, erupted by 6 magnitudes in the 1930s, and it's still very bright. The eruptions last up to a century. Okay, quite a fast eruption on a time scale of weeks was the idea. The XORs are kind of both of these categories described by George Herbig. He wrote the discovery papers. They are shorter duration outbursts, which are supposed to, the original ones lasted for between 200 and 400 days, also several magnitudes in eruption. But they're slightly more evolved objects. They're usually, all of these objects were detectable in visible light, but the XORs generally were objects with a later stage in evolution. There's no envelope left, it's just an accretion disk. And the FU Oris had a bit more circumstellar matter. Okay, so the numbers were small. And hardly any of these were optically hidden because they were selected in visible light. So when people started looking in infrared, I think about 5 years ago, Carlos Contreras, who was my student, and we started working on this stuff initially with UKIDSS, so we had 2 epochs and then with VVV. And at that time, there were only 3 of these deeply embedded YSOs known, which were eruptive systems, and now there's a whole load. There's even some class zeros, and there's one which is a massive protostar, which is unique at the moment, where so far it's a sort of low mass star kind of system, and lots of reviews on that. Okay, so this is the picture. Now the FU Orionis things, there's this perception in the community that you have a fast eruption, This is actually February, and it lasts kind of almost forever. So these were the three classical fuels, as they're called. And this perception of a fast eruption and then a kind of very long lasting event is a bit dubious, because the one in the middle was obviously not so fast, right? And the one here actually did decay partially on a reasonably short time scale. You know, so okay, it's time scale of years here, so it's not a short time scale, but it's still, compared to this one, it's different. So there are not very many of these events, and the outbursts were usually, even the recently discovered ones in the last 20 years, not very well sampled. So this is a chance for VVV to actually make an impact by discovering a lot of these things and actually hopefully having some sampling of what happens. Okay, why does it matter? Well, we think this might be a normal part of evolution for all normal stars like the Sun. They go through this eruptive phase when they're first born. It has a lot of implications for the formation of planets, for calculations of luminosity and mass of newborn stars in young clusters, which can be quite wrong if you just assume the accretion is gradual rather than goes in fits and starts. It may explain some long-standing problems. There's something called the luminosity problem, which has been around for nearly 30 years now, actually. It dates back to Scott Kenyon's paper in 1990. This plot is from a paper by Melissa Enoch and John Stauffer, where they looked at some nearby star-forming regions, and they just plotted the luminosities going from like, it's kind of, yeah, you see the luminosities on this axis as a function of bolometric temperature. So the colder ones are the youngest, most embedded objects. And you see that the theoretical plots of the dotted line showing how luminous they should be according to theoretical models, and the solid curve is showing kind of the median for each star formation region. And on average, when you look at the embedded YSOs, this is what we call class 1 protostars, which have a large envelope around the accretion disk. They're only a few 100,000 years old. These low mass embedded YSOs are much less luminous than the models say they should be. Okay. So one possible explanation is that they spend most of the time accreting slowly, and then there's a sudden eruption which lasts maybe 1% of the time, even if it lasts a century, and then it goes quiet for 10,000 years. You know, this is the classical idea, but we have no idea if this is true. Okay, but it solves these problems. Okay, now causes of these outbursts, well, we don't know. Lots of theories have been discussed. You know, theorists could spend an hour or more talking about this. Binary orbits, you know, gravitational fragmentation disks sending fragments falling in towards the central regions is a possibility. The accretion limit cycle that works in dwarf novae has been discussed. A mismatch between different processes moving material in from the outer disk to the inner disk could cause a overdensity to appear in a certain radius, which builds up until pressure forces it to suddenly dump matter onto the star. There's a whole load of theoretical instabilities which are not usually talked about in this way. Influence of planets is very much a new thing now, because ALMA has given us loads of data on newborn star systems showing that planets actually exist at an age, certainly giant planets at an age of 3 or 4 or 5 million years. We see them in newborn star systems. That was not supposed to happen, okay? Even at a few 100,000 years, when we look at these embedded class 1 YSOs, which have rising spectral energy distributions as you go into the infrared, definition of class 1, even those can have rocky planets. They probably don't have gas giant planets, but the models for at least the formation of a rocky core, which might eventually become a giant planet or might become an Earth, they often seem to work these days with a agglomeration on a timescale of a few 100,000 years. So even in these systems, we might be having shepherding effects in the inner disk caused by something like the mass of the Earth. Okay, so lots of difficulties here. So where we are, based on what we've done so far, we had 2 epochs in UKIDSS, and we had the first 3 seasons of VVV data. And so Carlos wrote a paper in 2014. I wrote a follow-up paper in 2017 with all of the UKIDSS eruptive, all the UKIDSS high amplitude variables. And Carlos, in his thesis, he searched VVV for everything that varied by more than a magnitude in the disk. Basically, he looked at about 120 square degrees of the disk in the mid-planes, this area, which is the area where there's glimpse data and Herschel data. And he made a catalog of 816 high amplitude variable YSO, high amplitude variable stars, that varied by more than a magnitude. And nice thing about this is the luminosity function of all of these. About half of them are YSOs. So this is everything in black, everything in star formation regions in blue. And we took out I looked at the light curves and took out things that look like Miras because they have nice smooth periodic things. Very simple thing to do. And if you get rid of the Miras, then you have this nice, it's possible to decontaminate the star formation regions and just see something which rises towards the faint end. So you have, in the field as a whole, it's bimodal. You have the Miras and you have the YSOs and a few EPs, but the YSOs are the largest group. There's also, yeah, a small number of EBs because they're not very well sampled. Okay, and some work has been done on high mass eruptive YSOs. Nanda Kumar was working at Hertfordshire, and his student now at Porto, Guillaume Teixeira, he went looking for massive YSOs to see if they also erupt. And interestingly, he looked at systems which should be massive YSOs because they're associated with things that trace massive star formation, like Atlas Gal cores and extended green objects. And he even found about 10% of their candidates, they were associated with methanol maser emission at 6.7 gigahertz. And that's supposed to be the most reliable indicator of massive star formation. And he found quite a few things that varied a lot in the YSOs. But then if you actually look at the ones where you know the distance of the cloud and you calculate the luminosity, it always came out less than 1,000 L-sun. Okay, so they're not that massive, not that luminous after all. It's kind of the definition of a massive young stellar object is if it's 1,000 L-sun, you're kind of entry level. If it's 10,000 L-sun, it's really luminous. And these things definitely are nowhere near 10,000, and they're generally less than 1,000. So we're learning a bit about how unreliable the kind of stuff that the high mass star formation people talk about. If they're not here, I can criticize them, right? Yeah. Okay. Anyway, so this is to show just how much these YSOs, they dominate the high amplitude variable sky in the infrared. You can see this most clearly just with the UKIDSS data, because this is 1,500 square degrees. This is my paper from 2017. The red dots are the things I thought were YSOs, and the blue dots is everything else. And that's just by spatial association. So I looked in Simbad, I looked in the WISE color images, and if things have within 5 arc minutes, at least 5 indicators of star formation, like Herbig-Haro objects, molecular clouds, that sort of thing, then I would say that this is a likely YSO. If it didn't, I would check the WISE color images to look at the lots of faint red and green stars, which look like young stellar objects. If there's at least 5 of those in the image, you say it's a YSO. And I checked this for false positives, and about 9 times out of 10 this is right, and about 1 time in 10 you'll get a chance association of something which happens to lie in a star formation region. So in the end, it's about 60% after allowing for that. It's not too bad. And the individual star formation regions, they just jump out. These are well-known regions, well-studied regions. W51 is 5 kiloparsecs away, and there's 9 objects hidden under that dot. So they're really tiny, sort of compact groups. Okay. So searches now to try and find more things, because most of Carlos's objects, they were embedded. It was exciting. He found, about 400 high amplitude YSOs. But some of the people who work on this field, they were not that impressed because they said, these are not FUORs, these are not XORs. Well, no, we didn't say that. We said they were eruptive. We even invented this tentative category of, we call them MNORs, because they had kind of mixed characteristics of shorter timescales of outbursts of a few years. And they seem to sometimes mix spectroscopically the characteristics of the F Orionis and the X Lupi or XOR objects. But most of the other distinction compared to the classical FUORs and XORs and what Carlos found is that he was going right down to 1 magnitude, whereas FUORs and XORs are traditionally things that erupt by 4, 5, 6 magnitudes, okay? And that no one had ever really looked before for things that only change by 1 or 2 magnitudes. It just had never been done. No reason for that, just no one did it. So most of Carlos's objects were between 1 and 3 magnitude eruptions. He had about 8 objects which were over 3 mag, but they were very much in the minority. So that's something we wanted to look for with the new PSF data and with the more reliable data, because Carlos had to select the most reliable sources. So he only chose sources with the best photometry to do his search. They had to have, stellar classification, low ellipticity in every single epoch for the first 3 seasons. So that gets rid of half of all the stars before you even start. So if you really want to search and be complete, you need the PSF, and that's kind of what we have now. So to actually find things, we use the Stetson index of the pore prints, and we use the von Neumann-Eater index, which actually Nicholas Medina was using in Valparaiso, and he showed us extremely effective. So both of these have worked very well with Lee's database, and both of these are included in the metadata catalog. So you have the indicators like interquartile range, but you also have the Stetson I index, and you have the von Neumann-Eater index. And if something has a high Stetson, it means that, the 2 pore prints taken in the same OB, they agree with each other. Okay, if something has a low von Neumann-Eater index, it means that the numerator is the difference between consecutive points in the light curve, and you want that difference to typically be small compared to the denominator, which is the overall variance. So it's nice and simple. The only real difference between Stetson and von Neumann is that the von Neumann doesn't require the 2 points to be in the same OB, any consecutive points in the light curve. Okay, but they work in the same way. So I initially did some searches of VVV DR4, which I've talked about at past meetings, but that was with the CASU database. So I found, I found another 24 or so high amplitude YSOs, but I wanted the PSF before I took this further, because I don't entirely trust the CASU stuff if it's not choosing the best photometry, but just trying to choose everything. So now with these data, we have the 8-year light curves, and they're deeper and better. And so I was able to do these searches. Now, just to show you how 8 years helps, this one was published by Lee. We thought it was in eruption here, but then we get the 8-year light curve, and you can see it's gone up again. So having 8 years kind of is helpful. This was another one which we published as a dipper. So we thought it's an extinction event, and then you get additional data when it erupts. And we actually have a spectrum of this one showing it went into outburst, and there's a FU Orionis spectrum. So sometimes you just have to have a long time series to understand what you're seeing. So this one is probably pathological. There's extinction and there's an eruption. But who knows? Okay, yeah. So the method to search Lee's database, basically, he has relative photometry calculated, calibrated locally within each array. So for every array, you've got, to minimize the RMS on the scatter, and he did that within each array on a local basis as well as just doing it separately for each array. So the relative photometry is about as good as you can get, regardless of any issues with the absolute calibration. And I selected candidates, well, I actually looked for variables and I looked for transients, but the main result was looking for variables rather than transients. And so I did a search for things that varied by more than 4 mag. They had either a high Stetson or a low eta or Neumann-Eta index. The median K, I had this cut, they had to be fainter than mag 11.25, and that was because essentially my previous work with the CASU database had shown that there was the distribution of candidates was bimodal. There was a saturated group which was brighter than that, and a fainter group which was mostly real. And so I just carried on using this number, and I retrospectively looked at whether this number still worked with the PSF. And actually, that to have fewer false positives, I should have gone fainter and maybe used 11.5, or But by going to 11.25, I had a slightly larger number to search, 248 candidates, but it meant I was more complete. Okay, and the other one, which is very important, if you're going to use VIRAC version 2, as Lee mentioned, half of the sources are not real because of all the things which are found near the bright stars, the halos of the PSF. Okay, so what you want is sources to be detected a reasonably large fraction of the time, so that you know it's a real source. So there's this parameter called PP2FRAC, is perhaps the easiest way to use it, and it just says that if this source is detected 20% of the time in the second most numerous paw print, because most stars are detected in 2 paw prints. Okay, so he ranks them by how often they're detected in paw prints 1, 2, and if necessary 3, 4, 5, and 6. And if the second commonest paw print has it detected in 20% of all the times when it should be detected, that's your PP2FRAC above 20%. Okay, so that's a fairly rough and ready sort of way of doing it. Okay, and the result for this particular selection is I had 176 real things out of 248, which is not bad, having looked at all those. In addition, there were 7 objects that were real variables, but the actual variability was less, and there was 1 bad data point, which makes it look like a high amplitude variable, was actually only 2 mag or 4. Okay, 65 which are not variable at all. So the real things break down into YSOs, cataclysmic variables, microlenses, Mara-like things, and unusual things. Okay, the bogus things are bright stars, where you have halo issues. But sometimes, yeah, it's just on the edge of a bright star. Asteroids, which we had noticed this problem before, that they lack asteroids. The ecliptic plane goes through the galactic bulge. So if an asteroid lands on top of a faint star, you have to go to the minor planet database and see why your completely normal faint star suddenly jumped in brightness by 4 magnitudes at one epoch, one time only. Okay, and the same asteroids seem to turn up actually. Ophelia and Crestmania, I know their names very well. Yeah. Blended stars and bad images. Hyperpromotion stars, we have about half of these are in Gaia and half of them are not. But you look at the image and you see the star moving through and landing on top of a faint star. So that's something we can fix in future once we've identified all the hyperpromotion stars. Defects at the edge of arrays, small defects in the chip, which I've not looked at too closely, but you've got some kind of bad pixel. And duplicate detections occasionally did show up. Okay, so basically with those 2 indices, Stetson and Eta, my initial selection was giving me all of this. And so I applied the Stetson and Eta cut to get rid of all the junk and just pick up the real variables which are here. So that's an obvious cut. And that was the real variables are filled in and the false positives are open circles. And so the stuff which is here, there's a few real variables with the high values of Eta, these filled circles here, but all of these cases are badly sampled. So you can actually, if you want to do almost a more complete more efficient selection is reasonably reliable, you can actually narrow my cuts and get rid of all this junk here, because even if it's really badly sampled, then you can't say what it is unless you've got another data set. So a retrospective ideal selection would look like this. And that's, you know, this particular selection would get, I've got the numbers, 168 of the 176, and it only had 8 false positives, which are hyperpromotion stars or whatever, and it only misses, you know, it's only missing 8 poorly sampled events. So you can actually narrow this down. And the benefit of knowing this now was that I was able to then relax my initial assumptions and go into a second search. And I removed this cut on saturated sources and did a search that found 3 more objects because I was doing a more focused kind of thing. Okay, so the transients, I also did a transient search, which I won't spend too much time on, but basically I looked for things again using Stetson and Anita, had a relatively small number of candidates, but we did find another, basically about another 16 objects which are not found by the previous search. And these are mostly novae, which are only showing up in, you know, a small number of epochs because they're only detected for a year or 2. And most of these transients are classical novae. Okay, so this is the breakdown, 195 real variables over 4 magnitudes. This is probably fairly complete for things that are well sampled in the 8 years of VVV. I think we have 60 YSOs, 59 classical novae. That's assuming that 9 of these transients that we've got in star forming regions are just classical novae. The rest are like microlenses, LPVs, etc. And the YSOs are my main interest, so that's what I'm planning to make the focus of a paper on this, is that we've got a majority of eruptive variables, a smaller number of dippers, which are probably extinction events, about 10 or so which are ambiguous, and just wouldn't want to say if it's erupting or if it's a dipper just by looking at like and one weird object, which is the one Dante and I were discussing, which has a sinusoidal-like curve. It's in a pre-main sequence cluster, and I think it might be, it's similar to KH15D or V582 MON in that respect. I think there's some sort of a occulting system probably, and a binary system that's being occulted by something that goes in front, because KH15D is quite to that. Okay, so to say a bit about the main scientific result for the eruptive variables. So here's 4 of these nice light curves for eruptive YSOs. So these are like 6 magnitude eruptions. So this is a lot higher than Carlos was finding in its initial thesis set. These 3 are quite well organized events, the top one on the left and here. And the big difference compared to the classical fuels is they're not far, you know, vertical eruptions. These are rising over 800 days, this one over 1,000 days. So this is new for the community, that these things actually have a slow rise. This one also quite slow, but a bit more noisy. Here's a few more. So this one also a slow rise, but there's something kind of periodic going on as it goes up and down. This one here, which has a slow rise and then a sudden increase. So there are things which are different shapes. Here's another case. We've got one which has a fast rise and then a slower rise. And this is like the single exception proves the rule. The only case which had a fuel-like fairly fast eruption. So that's more, they do exist, but they're not that common. We do have a few, I've shown this one at previous meetings, we do have a few brief transient YSO events. So this is one which was much shorter and was in an infrared dark cloud, and that's WISE data on the left and GLIMPS data on the right, showing this had a previous eruption in 2003 or whatever when GLIMPS observed it. It erupted here in 2013, and there's actually a 3rd eruption in 2017, which I'm not showing on this plot. So this one is a YSO. Okay, so to sum up the properties of the eruptive YSOs, if you plot the rise time and the post-rise duration, and this is very much preliminary numbers, but they're typically taking 2 or 3 years to rise, and then the durations are lower limits. They're lasting at least 5 years in total. So this is longer than Carlos's thesis set. We reckon they typically lasted 1 to 5 years, and we're looking at these high amplitude events. They're lasting more than 5 years, and they're taking longer to get started. So this is just basic facts. Periodic, but they're not periodic. Carlos had in his thesis quite a large number of objects that appeared to be periodic, although as we look at them now, we haven't systematically looked at all of them, but some of them looked periodic for 2 periods. The period does not continue. So we, again, benefit of the 8-year light curves. One more I should mention, very extreme eruptions, a record-breaking thing I picked up in WISE first and then recovered in these databases after looking at the saturated ones. 8.5 magnitude eruption of an object that is in an infrared dark cloud. The eruption's practically finished, so we got a spectrum of it. It's 8.5 magnitudes at 4.5 microns. That's the difference between Spitzer and WISE. In the near infrared, it's at least 6.5 because there's an upper limit from 2 mass. We got a spectrum recently from SOAR, or in fact, the director, and it shows a molecular hydrogen emission line to confirm it's a YSO. But there's no other traces of outbursts left because it's faded away, unfortunately. So here's some nice examples of occultations. So we do have these eclipsing events, a few of them. These three are nice and well organized, and it's like a star falling off a cliff. They just disappear as some sort of arm of a disk goes in front of the YSO. So natural explanations are you have a warped inner disk, which people are seeing with ALMA recently, or you have a circumbinary disk. And then there's also this one, just to show that they're not always organized. They can be really funky. You know, there's probably a PhD thesis on that object. It's another. If it wasn't, you know, if it wasn't in the star formation region, it would be a WIT object. But you know, we can just say it's another YSO with a funky disk. Okay, explosive events to finish off. So this is WIT-01, which Roberto mentioned earlier, and which you know, Dante was leading this, and we got a lot of follow-up data. But about a year or so ago, I said, Dante, please can I take over this one? Because I heard someone giving a talk. This was John Barley speaking at the Hans Zinnecker Fest in Edinburgh a year ago, last September. And so this was an object which blew up in 2012. It was the only red transient in the first data release, and it happened to be an infrared dark cloud. So I thought at the time, maybe this is just some unusually high amplitude eruptive event, and I didn't think too much about it. It wasn't until I belatedly got around to reducing some follow-up Spitzer director's time data that I got that I saw it was still detected in 2012, but it had faded by 9.2 magnitudes compared to the initial WISE observation in 2010. So 9 magnitudes made me think that's way more than an eruptive YSO. And the light curve, this is fading over 6 months. You know, it's fading like a nova or a supernova. It's a transient explosive event. It looks nothing like a YSO eruption light curve. So that made me think, when I saw that, maybe this is something different. And I was listening to John Barley talking about the explosion in Orion that happened 500 years ago, which is reckoned to be a collision between 3 or 4 stars. And this is very exciting because, you know, many people have observed the molecular bullets in Orion, which come out of effectively a negative object. And you can trace these stars moving away from the point of impact. These lines are shown here. This is the ALMA image, this is the near-infrared image. But it's thought to be one of the mechanisms why massive stars are created in the first place. It used to be thought there's no way to make a massive protostar because its own radiation stops matter falling onto it. That's no longer thought to be a fundamental theoretical problem, but it's still very interesting if massive stars do actually form through collisions. Now, there's no massive star where WIT-01 is now, but if collisions do occur, they should more often happen between low mass stars, because low mass stars are just much more complex. So I thought this might be true. There's at least 3 examples of similar objects known around the galaxy where we see the wreckage of past explosions. If this is true, we'd like to know. Well, I did have those 9 transients, as well as WIT-01. I carefully searched the database, and there were 9 transients in star formation regions. And I was initially quite excited by this because this one, knowing nothing at all about classical novae a year ago, this has this secondary rise. I've shown this one in previous VVV meetings. This structure here is real. I looked at the light curve and I looked at the images. It actually does this funky stuff. Okay, this one has these genuine perturbations in both images, both portraits. On the lower part of the light curve. This one has this jump and then the flat part and then the fade. So all of this was kind of new to me. But if you know about novae, and it's not actually that new. If you look at the 2010 paper based on the amateur AA VSO data by Strope et al., Richard Strope, there are individual examples in his set of 95 classical novae where they do this. And infrared nova light curves are different because you quite often see a peak, not when the optical burst happens, but 30 to 60 days after the optical peak, dust condenses at 1100 Kelvin in the shell, and you see the infrared peak. Okay. So actually, WIT-01, I did a fit to the SED, and it's perfectly fit by 1100 Kelvin black body radiation behind an extinction of 6 magnitudes. So I think it's a nova that happens to lie directly behind the infrared dark cloud. And to get the statistics on this, we have about something like 58 transients. 12 of them are in the GLIMPS-1 region, which is where the infrared dark cloud catalog is. So 12 of them could lie behind infrared dark clouds, which are classified. And if you check the chance of getting one of these behind an infrared dark cloud was only 1%. So that's why I was excited in the first place. But if you have 12 of them, the chance goes up to 11%. Okay, so now becomes, either it's something exciting like stars colliding or 11% chance just happened. So I have some radio data. I followed this up. It was actually followed up by some other guys in 2012, and I got a second epoch 2 months ago. And hopefully the fade in the radio data will distinguish between a nova where about 10 to the minus 6 solar masses is thrown off, and a collision between 2 stars where something like a quarter of the mass might typically be expected to be expelled. So that's my job, is to learn how to reduce radio data and hopefully come down one side or the other on that. Okay, so just to finish, what we've learned is that there are lots of eruptive variables. They're the largest group alongside the novae, and so I think we can write interesting papers about the infrared light curves of novae as well as YSOs. Most of the eruptive YSOs, they rise slowly on a timescale of years, but there are rare exceptions, more like classical fjords. The outbursts last a long time, and they're generally not periodic. And the variety of light curves, the sheer variety of the shapes that I showed there briefly, suggests you've got multiple processes. So more than one of those different unknown processes that cause, trigger the eruption are actually occurring, because we've got those very different looking bright, light curve shapes. And the spectra, Jen is going to be talking a bit about, but there's a lot of these objects we don't have spectra for yet. Most of them we don't. I did ask for director's time and got turned down, so we're going to have to go and hit these next year and hope they're still bright enough to actually get us good results on those. I think we may be able to see if the luminosity problem is true or not. If these objects are a solution to the luminosity problem, we can at least test that by, we don't know how long the outbursts last, so we can't easily get it, but we can do simulations and see if these are a plausible solution to the luminosity problem that I mentioned. And the protostellar collisions, well, we have these candidates, but I'm personally, with Occam's razor, I don't believe it at the moment. Most of those transients that I showed are actually relatively blue. They don't seem to have the colors of you might expect for a YSO. If there's a lot of circumstellar matter there, they just look like a nova would look like if it happens to be within a few arc minutes of a star-forming region. Witter 1 is kind of the exception that's behind an infrared dark cloud, which are relatively small patches on the sky and is much redder than the rest. But that's where we are at the moment. Thanks.
We have time for one question. Nothing.
Okay. These 9 objects, are they in Lee sample? Do they have parallaxes, for example? That will be.
They're all relatively distant. I don't think they've got Gaia parallaxes. Yeah, I mean th're all in the set that I circulated to you. So if you look in the category that says transient YSO, that's those 9, I think. So but none of these things have large pulse motions or large parallaxes. I mean, they're more than a kiloparsec away. So yeah, it's interesting stuff.